I will use English to the first words and then I continue in Italian. And it is a pleasure for me to give the prize, the Levi-Civita prize for this year to Professor Enrico Presutti for two reasons. The main one is because he is an outstanding researcher. The second one is a friend of mine. Proseguo in italiano. Allora, non parlerò del profilo, parlerò molto poco, due parole solo del profilo scientifico di Enrico Presutti, perché lui ha lavorato essenzialmente in meccanica statistica, nell'equilibrio, nel non equilibrio, i legami tra la meccanica statistica e la meccanica dei continui. Ha fatto moltissimi lavori, qualche libro, ha ottenuto molti risultati in questo campo. E cito uno giusto per ricordarlo, ovviamente ce ne sono molti, i lavori sono largamente centenari. Quello delle transizioni di fase. Transizioni di fase era in meccanica statistica, c'erano dei modelli su reticolo essenzialmente, c'era un modello molto particolare su continuo, ma molto particolare. Si deve a lui, insieme a Leibniz e Mansell, il mostrare che un sistema di particelle del continuo, cioè dello spazio fisico, può produrre transizioni di fase. Se ci sono cose particolari, cioè un esempio esplicito di quello che nota che uno si aspetta, ovviamente, ma non era dimostrato prima. Dopodiché ci sono molti altri risultati, è un profilo altissimo di ricercatori. Invece sul piano umano noi ci conosciamo con Presutti abbiamo fatto l'università assieme, quindi ci conosciamo dall'università, lui girava con una macchina scoperta, diciamo, cose che non la ricordo ancora. Poi ci siamo laureati assieme il relatore del professor Calogero, qui presente. Dopodiché le strade ci sono leggermente biforcate, nel senso che io abbiamo proseguito in due strade un po' differenti. Poi sapevo che lui si occupava di meccanica statistica, io di altri argomenti. Allora il professor Calogero aveva trovato un modellino molto bello in cui aveva tutti gli autostati, un completo, gamma completa autostati. Allora, nella mia ignoranza della meccanica statistica e le poche cose che sapevo dall'università, pensavo, vediamo di trovare l'equazione di stato, di fare il limite termodinamico di questo, quindi vai a vedere. Allora ho pensato di rivolgermi a qualcuno che lavorava in meccanica statistica. Errore in gioventù c'era Enrico che lavorava in meccanica statistica con il Cista-Larger, diciamo che continua a raccontare, che non è la maniera più semplice di affrontare la meccanica statistica, ma andava di grande moda allora, siamo alla fine degli anni 60. Allora abbiamo parlato, poi abbiamo fatto un lavoretto assieme provando l'equazione di stato esplicita di questo gas. Purtroppo il gas, l'equazione di stato non era così interessante, non era ovvio che non ci fosse una transizione di fase, perché la forza era unidimensionale, funzionava a lungo raggio, una forza a lungo raggio, quindi era fuori dai teoremi noti che escludevano la transizione di fase, però purtroppo non c'erano, perché era repulsiva il grosso della forza, mentre è chiaro che saranno quelle attrattive che possono eventualmente dare qualche meccanismo di questo genere. Comunque sia, dopo che per una decina di anni, oltre 10 anni, abbiamo fatto una collaborazione molto intensa con Enrico. Poi le strade si sono biforcate, noi abbiamo seguito la meccanica statistica del non equilibrio, non equilibrio, dinamica dei sistemi, dinamica sia deterministica, molto stocastica, limite idrodinamico e via. Poi adesso si è occupato, penso si stia ancora occupando del legame tra la meccanica statistica e la meccanica continua, facendo limiti opportuni e vedendo se limiti di scala e vedendo come funziona. È molto antico, molto interessante e ancora molto aperto. Volevo sottolineare un ultimo aspetto del carattere di Presutti, quello di coinvolgere le persone a lavorare, diciamo, giovani, se sono giovani, ma anche non giovani, anche persone che magari lavoravano, che hanno un salto di qualità lavorando con lui, lavorando sia di qualità sia di entusiasmo lavorando con lui. Perché è un aspetto della vecchia maieutica socratica di estrarre le informazioni, di coinvolgere, che è un aspetto estremamente positivo. E non parlo al passato perché Enrico ha dato in pensione, ma sta lavorando con la struttura dell'Aquila, è ancora completamente attivo, e quindi questa funzione notevole di maestro, in modo di portare le persone verso la ricerca, la continua a fare. Quindi dopodiché ho finito le cose e do la parola a Enrico per le sue scientifiche.
English. So at least sudden drop. And, so it's always difficult to talk after an introduction like this one. So I'll try to disprove what Carlo was saying. And when I gave the title of this talk, Lello asked me whether I wanted an extra hour. And no, I mean, I don't want to give a survey on stationary states in equilibrium and non-equilibrium. I just want to tell you some ideas I developed in the years about these features. That would works I've done, that would be too short for a talk. And then I will also tell you what I didn't do, but try to do, and still try to do. Okay, so let me start very elementary. So I'm going to talk about stationary states. So you would think of naturally of a configuration of X made of position of particles and momenta. And stationary means that should be a critical point for the Hamiltonian. So the velocity, the momenta will be zero. But I want to study stationary states which describe fluids at positive temperature. And one knows that positive temperature means positive kinetic energy. And so these states are not really good for such an investigation. So what one has to do is to go from stationary state to statistically stationary, which means that one looks for measures in the phase space with the property that if you take any set and you let it evolve for a time t, then the measures should be such that these two sets are the same measure. So one looks for such measure, and since the system is Hamiltonian, one directly knows that by the Lewis theorem that the measure px is invariant. But that's not good enough because I want normalizable measures, and this dx is only sigma finite because the momenta will be infinite. So one has to find an invariant measure, and one exploits the fact that the energy is conserved. So one can consider this measure, and this is invariant, and so one is active. But as I was telling you, one is interested in describing states, in studying states which describe macroscopic system. So I want to make the input that this measure should be looked at in a situation where the system is large. Now, mathematically, large doesn't mean much. The way one has to understand large in mathematics is to say that a system is large if it's not so different from larger systems. Or in other words, one has to study the limit of this measure when the system becomes infinite. Now, system becoming infinite means that the region that I'm looking at where I put the particle should have a volume which goes to infinity, and simultaneously the energy is also going to infinity, and the states which are interesting are those where the ratio goes to something. So this is the situation, and the classical result in statistical mechanics, I guess, from the 60s, is that indeed in this limit this measure converges to something. So one has the possibility to define stationary states in the infinite form. And one has also a nice characterization of these measures, because what happens is that if you take this measure and look at what's happening in a subsystem, let's say a configuration X which is here, and there will be other things outside, let's say X bar, and I condition, so I specify the configuration outside, then this measure here is modulo a normalization constant, the famous Gibbs formula, which is the energy of the configuration X in interaction with the configuration X bar. Okay, so this is a property that one can derive, prove rigorously, under suitable assumption on the interaction starting from this measure. And the idea of Dobrushin in the 60s was to look at this in the opposite way, that is, find measures such that their conditional probabilities are given by this formula. So these are equations which are called VLR equations. And there is a solution to these equations just by construction, because one has derived them by a measure. So there is certainly measures which satisfies this condition. But this is something strange, if you want, because same thing may happen in on the lattice. It's even easier to describe it. And in the lattice you have spins, so the equivalent of this will be the measure of the spin at X given the spins outside is given. So this was a point Carlo didn't mention in his talk, but that was the thing we were discussing in the 80s at EHS. Because once you have this formula, then you think, okay, let's, this describes equilibrium, homogeneous equilibrium, but suppose you want to describe the Fourier law, when there is a flux of energy, so the temperature is not constant but depends on X. So we were saying, okay, let's put an X here. And then find a measure that satisfies these conditions and everything. And we were happy because once we discovered this, we had a formula not only for the equilibrium but also for the non-equilibrium. But I mean, it didn't work because it turns out that there is no solution for this. So it's very strange, but here, if beta is constant, everything works. If I take a beta which is varying, there is no solution. And I mean, this has been still very much studied, and there are ideas, indications, let's say, that there is still a Gibbs formula like this one, but the energy is not the original energy of the particles, but there are extra potentials, and these extra potentials are very long range. Long range. So this means that the correlations, the interactions and the correlations in stationary states which are not equilibrium are very, very long range, very different than in equilibrium. But I mean, I'll maybe come back on this at the end of my talk. So I mean, if you try to present the equilibrium statistical mechanics the way I have done, you should notice that I didn't mention ergodicity, which is instead very typical in the textbooks about statistical mechanics. Here I've avoided the question. And I mean, if you read the Landau-Lifshitz book on statistical physics, you find a note where they say that ergodicity doesn't have much to do with thermalization in macroscopic systems. And the way they explain it is something like that. To take a subsystem of the full system, then its thermalization is not due to the ergodic properties of the gas in this system, but rather to the fact that this subsystem fills the environment, and the environment is very large, and so all fluctuations are possible, and so this system will be subject to all kind of possible interactions, and that's the way it thermalizes. You should think of a small boat in the sea, in the ocean, and then what it's done is essentially determined by the waves, the large waves which come from very far away and create this its behavior. I mean, this is vague, the way I'm saying, but actually was used in a proof, in a mathematical proof. That was a paper I was involved with Carlo Boldrighini, Sandro Pellegrinotti, Sinai, and Soloviecic many years ago. And I just mentioned something of this because can I use this for a raise? We were considering a very simple system, which was on the line from 0 to infinity, was made by point particles. The first particle had a mass m, all the others had the same mass, small m, and the only interaction was elastic collisions. And we wanted to prove some ergodic properties. I don't want to enter into that. Essentially, the thermalization means that what we had to prove was that if you take a configuration, let's say like this, with velocities, let's say anything in some domain, and then I take another one, maybe with more particles, then its evolution will be determined from what it's coming from the right. And what we had to prove is, so think of the particles which are coming from the right as bullets, and you are firing. And then the question was find a firing strategy so that after you have done that, the configurations in these intervals, starting from here or from here, are essentially the same. Now, so the question was find a rare event such that leads the system to a definite situation independently of what was it before. And that reminds you of the thing I was saying previously, that a subsystem experiences everything, and so it will experience after some time something that you want, and that leads it to something which forgets the previous history. So that was the thing I wanted to say. I mean, it's very vague, and but if you are interested, we can go back to this. So let me go back to the main topics, which was the stationary equilibrium. And as Carlo was mentioning, one of the things which are interesting are phase transitions. So phase transition in this language means the following. I was saying there exists, there is convergence, and I was sloppy at this point, because this convergence exists, but in general by subsequences. It's not sure that there is convergence. Or in other words, if you look at these DLR equations, it's not sure that there is a unique solution. Existence is granted by the construction, but uniqueness is not. And physically, one relates the non-uniqueness to phase transitions. One knows a lot about the structure, the possible structure of these limit Gibbs states. For instance, one knows that they are a convex set in the space of all probability measure, but for instance, it's not something like that, but rather like this. So one knows that something about the structure of this, but what it's really missing is when there is existence and when there is not. So this is an open problem in general. There are answers in the lattice case, and there are very few answers in the continuum. So let me tell you a little bit about this. So the phase transition that one thinks it's very complicated. It means that there are special values of temperature and external parameters for which the system, the fluid, stays in completely different situations. For instance, could be liquid or could be a vapor. And now there could also be solid, as we see around, but the transition to solid is very difficult. So let me talk about the liquid-vapor phase transition, which is the easiest thing to understand. And the van der Waals theory is a key point in this, in understanding this phase transition. So you know that perfect gas is something for which PV is equal to NKT, pressure, volume, Boltzmann constant, number of molecules, and temperature. So this is the perfect gas, which means real gas means very low density, very high temperature. So it's something extreme. if you have a real gas, there will be corrections. So one correction comes from the fact that there is an attractive interaction among molecules, so that the pressure exerted by the gas on the walls is smaller because there is an attraction. So in this formula, you add a term like this. Rho square is the density square, so it's proportional to the number of pairs. So it's proportional to the interaction. Alpha is the strength, the average strength of the interaction. Okay, N is, so how you put it? N is N. I cannot correct it. The other correction comes from here. It's because this is the volume available to the molecules, but the molecules have some size. So you should here subtract the total size of the molecules, and you get a formula like this one. So this is the van der Waals formula, and if you plot it, you find that there are this is a constant temperature, and then you have things like that, which are not physical, as you know, and should be replaced by the Maxwell rule. Like that. So this naive argument plus this Maxwell rule gives isothermal curves that are this form. Go from the perfect gas into something which has this discontinuity, and here there is a phase transition. So this was the theory, and then the question raised in the 60s by Katz was, is there a possibility to derive such phenomenon from statistical mechanics? So find an interaction for which this works. And the point was that if you study a system of hard rods, so particles which are some size, the size, let's say, is A, and you put them in a box, and then you put a mean field interaction. So each one is interacting with each other with strength alpha over n. Then if you apply statistical mechanics to the system and you do the thermodynamic limit, you get exactly this thing. Okay, so what is bad in this is that the interaction depends on the number of particles, which is unphysical. So the idea of Katz was, let's try to find something similar to this, which gives the same result. These are the Katz potentials that I want to mention because then I've done something on that, and it's interesting to say something. So the idea was to put an interaction between particles which has this form, minus alpha, then potential which depends on gamma. And that's the interaction between particles at position r and r prime. This gamma is the Katz parameter, and this is equal to some gamma to the d, let's say, a fixed j, positive, and then gamma r minus r prime. So that the interaction you see is very long range if gamma will be something very small. Positive but small. So the length j, let's say, is a function of compact support. So the range, the support of j gamma is order gamma minus 1. So it becomes very, very long. But its strength is very small, gamma to the d, which you should compare with this 1 over n, which is here, of the mean field. And so this is a good system from the point of view of statistical mechanics, because it's a compact support interaction, but at the same time has features of the mean field, because if gamma is small, there are a lot of particles interacting with each other. And what Katz proved was that indeed in the limit, in the thermodynamic limit, and then in the limit as gamma goes to 0, one recovers the van der Waals theory, with the Maxwell rule included. So it was a big success from some point of view, but from other point of view was also a failure, because if you take the limit, in the limit gamma to 0, this is no longer an interaction. Doesn't make sense. And if gamma is positive, it's not clear that you get the same thing, the same phase transition that you get from van der Waals. And indeed it doesn't, because there is rigorous proof that in one dimension for finite range interactions there is no phase transition. So indeed Katz proved that there is a phase transition as gamma goes to 0, but any physically reasonable statistical mechanics model doesn't have the phase transition. The idea was, of course, to try to extend this to 2 dimensions, where the general theorem about absence of phase transition doesn't exist. But at that point you miss the simplicity of the model, because if you go from r rods into spheres, then it's very difficult. The system becomes too complicated really to be studied. So there were proofs that also in more dimensions the Katz result extends, so that if you do thermodynamic limit plus gamma goes to 0, then you recover a phase transition like van der Waals. But one couldn't say anything about gamma small. So I have a paper that Carlo mentioned with Leibowitz and Mansell, where we were able to prove a phase transition, but the idea there was to replace the rods by another Katz potential. So in that way we were able to avoid the difficulty of the small scales interaction which are present when there are rods. And we tried. The idea was then to try to see what happens if we try to put to add to these Katz potentials some so that was the LMP model. Leibovitz, Mazel, and myself, which is described by an attractive pair potential and a repulsive four-body potential. To this one can add our cores. This was done by Elena Pulvirenti and Dimitri Tsakarogiannis. But that was not a trivial extension because required to prove, this is technical, I'm sorry, but required to prove cluster expansion results in the canonical ensemble, which was not known. But still one needed this LMP interaction. What I'm trying to do now, what I discovered, I should have before, but I discovered a paper by Katz and Delfand, which proposes a very nice thing. Still, you see, the only thing that I can treat are one-dimensional rods. If I go to more dimensions, I'm lost. But I have to go to more dimensions because otherwise, when gamma is finite, there is no phase transition. So the compromise in the Katz-Delfand was to consider a system made of layers, where on each layers you have rods, and then you have a very small interaction among layers. These have some physical interest, because these are models where you have patterns, horizontal patterns, and then that can slide one with respect to the other. So these are physical systems where there is this strong interaction and very little things, so that they can slide one on top of the other. And so, for instance, on each line I put this interaction among our rods, and then I put local, very small interaction between nearest neighbor layers. For instance, with strength, which is gamma to a large number. So large number, 100 is a large number by definition. So this is the kind of interaction that I'm putting, so that in the limit as gamma goes to 0, this interaction doesn't play any role, and the thing slides one with respect to the other. And then the question is whether with this term on top there is really a phase transition. Okay, so there are several difficulties. The very main difficulty is that in order to repeat the proof which is here, I need to prove some cluster expansion estimates for this system. And now on each line I have a rods, but unfortunately the densities at which I will have a phase transition is such that for that density the hard rod system doesn't have the cluster expansion doesn't work. But on the other hand, it's a system of hard rods, so it's maybe possible to do something. This is my exercise for Christmas. So I don't want to say much more about this. What I can say is that the small interaction among layers, this can be understood that it's under control. And there is recently I've done a paper with Titi Merola, Maria Lalia Vares, Domingo Marchetti, and Roberto Fernandez, where we have proved this result for the Ising case. So here are Ising spins with Katz interaction in this direction, and this gamma to the 100 nearest neighbor interaction vertically. And for this we can prove that there is a phase transition. And the reason why this gamma to a large power doesn't really play a role, it's simple to understand. Because if you take an Ising model with Katz interaction by itself, then you have a magnetization profile which is something of this sort, where this length is of order e to the gamma minus 1. And also that the fact that there is no agreement between two nearest neighbor layers means that there is an interaction which is of the order e to the gamma minus 1 times gamma to the 100. So it's very small. So unless this is exponentially small, thing works. Okay, so let me, I guess when I started working on statistical mechanics out of sister algebras, as Carlo was saying, we had strong influence from Giovanni Gallavotti. And one of the things that at the time Giovanni Gallavotti was saying is that if something is interesting or right or correct, it's an Ising model, or it's reducible to an Ising model. I mean, anything else doesn't work. So it's, let me give an example of that. So I'm kind of changing subject in a sense. So let's consider a stochastic PD of this sort. du is the Laplacian of u minus u cube dt plus d log group 1. So this is stochastic PD. U is a scalar, and it's driven, if there was not a white noise in space and time, this would be a reaction diffusion equation. So there is the diffusion delta U, and then there is an attractive force towards zero. So without this, U would be zero. Now what happens if we put this noise? So this is a difficult problem. In D equal 1, it's not difficult, because the white noise is sufficiently regular and one has a solution easily. In D equal 2, and D larger than 1, the noise is irregular, it's kind of a distribution. And here we are taking powers of distribution which doesn't look nice. And there are results. In 2 dimension it's well studied. It's D'Aprato and Zabchitz. Don't record this part. In 3 dimensions, it's much more difficult. The result is due to Martin Harrier recently, and it's a local in time result, and it's very, very hard. It's what he does is to do a Taylor expansion at each point, and then he has a way to patch together all these Taylor expansions and construct a solution. And the difficulty is that this is really not well defined as an equation, and indeed the solution is obtained by changing a little bit this equation by adding terms which are infinite. So this is just to scare you a little bit about what's happening. There is a relation of this equation was also studied as a stochastic quantization of the Euclidean quantum field theory. That is, the stationary state of this equation is e to the minus integral of u4 in the x times the free measure. Okay, so I gave you a very vague idea of this problem and tried to make it as scary as possible, because now I want to say this is related to the Ising model. So for the Ising model, so here there is a dynamics. So the Ising model, so I'm studying Ising model with Katz potential. So the interaction is minus sum x y gamma to the d j gamma x minus y. And besides equilibrium, one can define a dynamics. It's so-called Glauber dynamics, for which spins flip, and flip at a rate chosen in such a way that the Gibbs measure with this potential is invariant. Then if you do that and you study the system on the scale, so you study the system on a scale where the lattice mesh is gamma, then you derive an equation which is an equation for the local magnetization, which is given by this formula. Okay, so I want now to relate this to this. So I consider, so first of all take, so the critical value of beta is equal to 1. Just take m, which is a constant in space, and then you find out that solutions, that if beta is smaller or equal than 1, the only solution is m equal to 0, otherwise there are more solutions. So let's put beta equal to 1. And then let's expand this around m equals 0. So I will get minus m plus j star m. I'm supposing here that the integral of j is equal to 1. So this is a non-local Laplacian. In order to get the u cube, I should go further in the expansion of this.
Sorry, what is the dynamics?
The dynamics is Glauber. So it's spin flip with the rate given by this in such a way that the Gibbs measure is invariant. There are several Glauber dynamics. One of them gives this equation. Okay. So one has something of this form, and then can look at corrections. So if you were here, so something like 10 days ago, there was a seminar by Sergio Albeverio at the Tirozzi's conference, and he was saying something similar, saying that the next term that you have to add is something of this form. Okay, so the idea I had was this one. Okay, let's look at this equation. So this equation describes the fluctuations around m equals 0, which is the stationary solution of the original equation of this one. And it's done by something where there is this Laplacian, but there are these fluctuations. So since there are these fluctuations, they will grow in time, because anything can happen. So sometimes they may grow. If they grow, then m increases. But if m increases, this approximation is no longer valid. So it means that I have to take the next term here. If I take the next term, I get an m cube. If I get an m cube, I'm done. Not because I have an equation where I have simultaneously a fluctuation and the m cube. And so I'm deriving this kind of equation. I mean, what else? Okay, this doesn't work, unfortunately. So let me explain why. Now, first of all, should say that in one dimension it works. In more than one dimension it doesn't, because one should do something else. And the something else is the interesting part that I want to tell you. So let me say how am I doing with time?
You have 15 minutes.
15 minutes. I'm sorry for you. So it's let's do this game. So when time, let's say you have to look at long times. So when time grows, the fluctuations spread around, and so let's look at. So in a time t, I'm looking on this scale. The spread due to the Laplacian, this is kind of a Laplacian, it tells me that distances are of the order of square root of t. So the correlations grow like square root of t in space. So let's take a volume of the order square root of t and try to compute the average of u square in such a volume. So this means that I'm taking in this volume, I'm summing all the spins divided by the volume and see what's their value, typical value, by doing the average of u square. Where I'm doing this computation with this object. Then I'm getting
What is u?
what is?
U.
U is the is this. I'm shifting, sorry. U was here there. Okay, so this is the average magnetization. It's the empirical magnetization squared in that volume. So this grows like gamma t to the 1/2 in one dimension. Gamma square in 2 dimensions. Gamma cube over t to the 1/2 in 3 dimensions. So this means the following, that here in this volume it's really increasing. No? No? So it's getting larger and larger. If I'm in 2 dimensions, it doesn't increase in time. But what's happening is that it's still very extended in space. And even worse here, because in 3 dimensions it's decreasing in time, but still it's very long range. So what should I do now? I mean, I want to compare with the so if now I have this u, I want to see whether the next term in this expansion is comparable to this. So I have to look at, let's say, u cube times t. So that would be the average drift due to the next order term here. Okay, so and I want this to be of the same order as this one. Okay, so I'm getting in d equal 1 that u comes of the order of gamma to the 1/2 and t of the order of gamma to the minus 2/3. So if I want this term to be comparable with this one, I'm getting that u should be gamma to the 1/2 and t this. Here should be u gamma and t gamma to the minus 2, and here u order gamma cube and t gamma to the minus 6. In other words, I mean, maybe you didn't follow this heuristic argument, but by equating the increase due to the stochastic part and the increase due to a drift of order u cube, I would get that these two are comparable, are on the same scale, if u is gamma to the 1/2 and t is gamma to the minus 2/3, or gamma minus 2 or gamma minus 6. So this leads to the conjecture that if I look at my Ising spin system with Katz potential on this time scale, I should see fluctuations where drift and noise compete with each other. And so this is correct in 1 dimension. This was something I did several years ago with Lorenzo Bertini and Barbara Rudiger, and then it was also done by Barbara Rudiger and Joseph Fritz. In 2 dimensions is incorrect. This was something that was done with Marzio Cassandro and Rossana Marra, again several years ago. And it's interesting to understand why it's not correct and what should I do in order to make it correct. So the reason why things do not work, let me erase this part. Dici? Okay. Yeah, maybe. Good. So what's happening is the following, is that if I do, let me see whether I wrote down. If I study the correlation u square locally, so in volume of order 1, then I find in d equal 1 gamma to the t to the 1/2 order, here I find gamma square log t, and here I find gamma cube in 3 dimensions. So if you compare with the averages in the large volumes, in 1 dimension they are the same. So it means that the fluctuation field locally has the same order as in the big volume. If I look in 2 dimensions, instead I see, in the large volume I see gamma square as the typical size, but locally I see gamma square log t. So it means that locally the field is infinitely larger than the field that I want to study. And now here is the source of the trouble. No, because here we have, if I expand this, I'm getting the next order will be the cube, but it will be j convoluted with m. And j is of the order 1 because I'm gamma x. So the thing which appears here is the average of spins, if you want, of magnetizations which are close by to each other. So when I'm averaging U cube, how should I say? It's difficult to say. When I'm averaging that, I'm averaging, let's say, sigma x prime, where these are at distance gamma minus 1. So, I mean, my point is that if I'm taking an average of cubic terms like this, I'm not getting the cube of the averages, but I'm getting something which is different. And if I do the computation with a Gaussian term, I will get the average will be 3, because there are three fields. Then C 0, which is this term, and then I'm getting a U. So, said it badly. I mean, let me just say the conclusion. The conclusion is that if I'm taking the third order term and I take the average over the big volume as I was doing here, I'm not getting the U of the volume to the cube, but I'm getting this term. And this term, if you see, as a C0, which is gamma square log t, and so there is a log t more. So what we proved with Marzio and Rossana was that indeed at this point we have just Gaussian fluctuations. The cubic term doesn't appear because it's replaced by this one. So this term is killing the effect that I want to see, and I want to eliminate it. So how can I eliminate this term? Well, the thing I can play with is the beta which is here. No, because if I was putting beta equal 1 in order to have this, but now let's put 1 plus something. Then I'm getting this term plus something times m. And if I choose this something exactly equal to C0, then I can cancel this term. 3C0 actually. Now, so a shift in temperature, I increase beta, allows me to kill the factor which was here and which was preventing the cubic term to appear. So this has, it's well known in in the literature. This term is the weak correction to the cubic term. In 3 dimensions it's even more difficult, and I won't try to explain it to you. But the point is that this is a nice conjecture. That is, that if I put myself with this temperature, then I'm getting this equation, at least in 2 dimensions. And I'm periodically announcing that I have a solution to this problem, and I find out a mistake. So at this stage, 2 days ago, I had a solution, and it doesn't work. Okay, so I think I can stop here. Thank you very much. So if you have questions, if you want.
Questions?
Alessandro.
Can you comment a bit more about the DLR equations with the long-range Hamiltonian?
Yeah, that's that's something that has been done by so the results refer to the case of one-dimensional symmetric simple exclusion process with sources, with different sources at the boundary. So these are particles which jump independently, with the only fact that they cannot jump over occupied sites, and there are a birth date process here and here, and they have different rates, so that it establishes flux, and it can be proven quite easily that there is in the limit as the length n goes to infinity, there is a linear profile. Then Leibowitz at some point asked the question, I mean, what are the large deviations of this measure? And the conjecture, since one proves that locally it's converging to local equilibrium, the natural conjecture was I mean, there will be the large deviation will be the sum of the large deviations for the equilibrium states corresponding to each point. And instead, there was proved by Derrida, Leibowitz, and Speer that this is not the case. That is, that the large deviations of this system are a very long range. The structure of this interaction is more general. There is a general theory due to Bertini, De Sole, Gianni Iona, Davide Gabrielli, and Flavio Landin, that indeed there is this interaction, this emerging long-range interaction can be found in terms of an Hamilton-Jacobi equation. And the fact that in non-equilibrium there are long-range correlations seems to be a general belief. There was, Leibowitz has always been saying that, and there was an old paper by Leibowitz and Christian Mais who made an argument for that. So it seems that it's just equilibrium is a very special case for which there are cancellations for which the correlations are short range. But if you take a system and you have to guess, it's better you guess for long range correlations.
The pattern with interacting parallel lengths should somehow similar to a strongly anisotropic square lattice.
Yes. Yes, it is. It is, I mean...
It's like having a very small space, spacing in this direction and a much larger space in the water, and also in this direction.
Yeah, I mean, it's... I mean, this was... I mean, one way to look at this question was this one. Okay, let's take easing or any other things, let's say on the square lattice. Now, if it's isotropic, so each spin is interacting, let's say, with its nearest neighbor, then if the interaction is large enough, there is a phase transition. Okay, now suppose that you do the following. You take a distance of the vertical interaction and you put it on the horizontal one. I mean, if you keep doing that, in the end you have only horizontal interaction and you don't have any more a phase transition because it's one-dimensional. So is there a critical value at which this thing changes? This I don't know. I mean, that was one of the way I was looking at this problem of the layers, whether you can, how much freedom there is to go from isotropic into anisotropic. So from what I was saying, in the case of Katz potential, you can allow anything small enough, provided it's a power of gamma, and it works.
Okay. You said that this is a stochastic question. I just want to know if you tried some numerical scheme to see if you could find some solution.
Yeah, I mean that. I mean, this was one of the appealing thing of this approach. I mean, you have. I mean, from what I was saying, here you have the size of the system and the time you have to wait in order to get presumably what it's this equation. No, this is a discrete system. Also the dynamics could be discretized, so it's everything can be put in a computer in principle. Now the point is that I imagine that it's not easy to do it. I mean, I don't know whether it's too much for a computer. I mean, these are big sizes. So I don't know about the implementability, but in principle it's a finite volume effect. So it must be done. I mean, in principle it's doable. And the fact that I mean, maybe one has to wait for gates to the power 3. It's something.